system of equations by graphing? First of all, it would be kind of nice to know what does it mean by a system of equations. Here's the definition right here. Two equations in two variables are called a system of equations. So when two or more, we're only going to work with two, when two or more equations have to work together, and there's more than one variable involved, such as we're going to have x's and y's, we're going to be solving not just for one of those variables, but instead we're going to be solving for both of them. So two equations in two variables are called a system of equations. And oftentimes the reason we work with two equations or more together is because it's the only way to problem solve when there's more than one thing to solve for. So it's very useful when there's a couple of things needed. So to estimate, and I say estimate, that's why we're going to do check problems, because we're going to just look at the graph and say, this is what I think it shows. The solution of a system of equations using a graph. We're going to determine the point of intersection. Where do each of the lines cross? Point of intersection. We're going to be looking for where are those lines crossing. Now they don't have to be perpendicular lines, but we know perpendicular lines intersect, right? What are the only two, when we have two lines on a graph, what are the only types of lines that will not ever intersect? Let me think, what are the only types of lines that no matter what you do, you're not going to get them to intersect? What do you think, Brighton? Parallel lines. Yeah, parallel lines aren't ever going to cross. So then we would say, well, there's no solution for that system because we are looking for the point of intersection. So we'd like you to fill in, what does a point look like? It has an x value and it has a y value. Okay, here's our system of equations, the two equations that are going to work together. We have y equals 3x plus 1, and then we have y equals negative x plus 5. So we're solving by graphing. So we're going to graph each of them, and we're going to graph, okay, again, hear me on this one. I remember saying this when we were doing parallel lines on a graph and when we were doing perpendicular lines on a graph. I said, graph the points for one of them, and then do what right away? Draw the line. I guarantee you, if you don't do it on this one, you're going to get messed up. You need to make sure, draw that line before you move on to the other line, okay? So we have our first equation, which is y equals 3x plus 1. Is it in slope-intercept form?
Yes.
Okay, so we're ready to identify m and b. What's m?
3.
3. What's b?
1.
1. Okay, so we're going to go graph that one right away. Before we even take a look at that other one, we're just going to go graph that one. So we're going to go and put its starting point on and use our slope to get at least, we're going to try always to put a minimum of 3 points unless the graph will only hold 2 for that equation, okay? Sometimes the graph isn't big enough to hold the coordinate plane. So 3 points at least. This graph would actually hold 4. The more points you make on these, I guarantee you probably the better estimated solution you'll make if you get yourself as many points as you can. And then draw your line through it. Okay, I'm going to do another one of those. I'm going to try again. And arrows at both ends because we know it goes on forever. Okay, so we have one of our equations from our system graph. Now we'll go back and work with the other one. So y equals negative x plus 5. Is it in slope-intercept form?
Yes.
Yes, it is. Okay, so then we can go to identifying its slope and its y-intercept. What's its slope?
Negative 1.
Negative 1. And what's its y-intercept?
5.
5. Okay. So go ahead and get that one graphed. These would be one of those that maybe you want to make, because it's got a, you don't go very far for the rise and run. It might be a good idea to make a bunch of points. In this one, you can only use the slope in one direction, can't you? Okay, so today we're not just graphing to practice graphing, today we're graphing to find the solution of those two equations working together. In other words, we're looking for the point that will make both of them true. It's on both of the lines, in other words. So what is that? What do we think the estimated solution is? What does it appear to be? Cameron?
1, 4.
1, 4, because they're intersecting right here, aren't they? So ordered pair 1, 4. So first of all, when they ask you to solve it, you have to give your solution as an ordered pair. It shows an x value and it shows a y value, because there's x's and y's in both of these equations. So we're looking for the x value and the y value that will make both of them true. So we're going to write down both equations. Y equals 3x plus 1. That was one of our equations. Because now we're going to do we're doing a check problem. We're checking to see if this is really the solution. And then we're going to put it into also our negative x plus 5. So let's just do one at a time. What are we going to put in for y?
3. No. 1. 4.
4 in for y. The y value of our point of intersection. So 4 is going in for y. What are we going to put in for x? 1. And this is not just do it because it's part of the requirements. This is to really see if it's going to make it true or not. If we didn't graph it right, it shouldn't check out. But if we graphed it right, then we should have the right solution. Okay? And that's what we're checking right now. So 4, can't do anything with 4. 3 times 1?
3.
3. We're still not done.
Plus 1.
Now we say 4 is 4, equal is equal. 3 plus 1 is?
4.
4. Can't do anything else. Now we ask ourselves, is that true? Does 4 equal 4? Did we end up with a true statement?
Yes.
Yeah, so this one checks, okay? But it can't only check in that one. You don't get to stop there. You have to make sure it checks in the other one also. So now we'll put it into our x and our y into this one. So we're going to put 4 in again for x, and 1, I'm going to show parentheses here just to show that I substituted a 1 in for that x. Because that negative sign is not part of the x, it's in front of the x. Okay? So now we have 4 comes down, equal sign comes down. This is kind of like saying, what's the opposite of 1? Negative 1. And then we bring our 4 down again. We're not solving, we're just kind of like putting in, substituting in, simplifying until we can't do anything else. What's negative 1 plus 5?
4.
4. Because it is 4, because we want it to be 4. It is 4. Negative 1 plus 5 is 4. And so we can say this one checks because we end up with 4 equals 4. That is a true statement. So now that it is checked out in both of them, now we can say to ourselves, I'm feeling good about what my solution is. If it doesn't check out let's say it checks out in one of them, but it doesn't check out in the other. Should you move on? No. Something went wrong. You need to go back and say, okay, well, it didn't check out, so you can either, first thing you can possibly do is just check your check problem over, make sure you didn't do something silly like saying negative 1 plus 5 is negative 4. You could be something like that you made that mistake. Or you could go back and look at your graph and make sure, did I have the right slope and y-intercept, and did I use them properly on the graph? And then maybe it was one of the lines was actually graphed wrong. So we're going to say that the solution is ordered pair 1, 4, because we checked it out. It is the only ordered pair that would satisfy both equations. We could try all day other ordered pairs, check them in the two equations, and we would never find other ordered pairs that would satisfy both of them, would check out in both of them. Anybody in here think they can give me one ordered pair that would work in one of them but not the other? What do you think? Do you think you can come up with a point, an ordered pair from our graph, that if we did a check problem, you'd say it would work in one of them, but it wouldn't work in the other. Ariel? 0, 1. Okay, so 0, 1 on the graph is right here, this one right here. So she's saying that this one would only check out in one of them. And why would that be, Ariel?
Because the other line on the graph doesn't pass through that point.
Yeah. The other line doesn't have that point. Only this one has that point, not the other one. So it would check out in this one, but it wouldn't check out in the other one. So we wouldn't be able to qualify, that would not qualify as a solution to the system. It's a solution for that one equation all by itself, but not for the other. And they are working together. So it has to satisfy both. Okay. So Trey, did you have another one for me?
I was just gonna say,
Any
any point where the line does not intersect.
point that's on one of the, yeah, and what if I chose this point? What if I chose, over here, -4, 0?
None of them
Would it check out on either of them?
would.
No, wouldn't check out on either of them because it's not on either line, is it? Okay. Now let's just do a big case. Isaac?
I'm not following on the 1 and 4. We're gonna be switching around.
Okay, here's the deal. This is what your brain wants to do. In the ordered pair, the x value comes first, doesn't it? And then the y value is the second number. But in our equation, what comes first? The y. So our brain wants to put the first number in for y and the second number in for x because of the order. But we have to override it and say, wait a minute. Even though 1 is first in the ordered pair, it can't go in for y because that's not a y, that's an x. So you're going to have to, like retrain your brain there. Okay? So here might be a thing you could do that might be helpful. Go like this, say x, y, and then you could say, okay, now when I look up to my ordered pair, I'm going to put 1 in where the x is, and I'm going to put 4 in where the y is. So we just have to make sure just to substitute back in the right spot. Okay.
But if it's 1, 4, would you go up 1 to the right 4?
No, this, I can't.
Oh, from naming the ordered pair. Yeah. Okay. Okay, I want to do another just really quick review with you. Okay, when we have a positive slope, what should the line do? Rise from left to right. Everybody, I have so many unengaged people here right now. Wow, you're gonna run into trouble on your assignment. Okay, so are you ready to engage here? Okay, positive slope is going to rise from left to right. Dakota, negative slope is going to
Fall from left to right.
fall from left to right. When there is a 0 slope, what kind of a line will I have? Brighton? Okay. I want to talk about just the line's behavior first of all, and then we'll talk about its equation. If it has a 0 slope, what kind of a line is it? Trey? Horizontal. And what's missing from the equation in a horizontal line? The x's are missing because 0 times x, they're gone, remember? So when you have y equals a number, you have a horizontal line, right? With no x's in the equation, horizontal line. What kind of a line do we have when there are no y's in the equation? Then we have a vertical line. X equals a number means you better draw a vertical line on your graph. So what if it was x equals, let's say, 5? How would you graph that then, if it's x equals 5?
You can put a starting point off that, but it's just.
Where would that starting point at 5 go on? Which axis?
The x-axis.
In the x-axis, because it crosses the x-axis. All the x's are 5. So you're going to go to the x-axis and you're going to put a 5. You're going to put a point at 5. And then you're just going to take your ruler and draw a vertical line going through it. When there are no y's in the equation, we're going to have a vertical line. And we're going to start on the x-axis instead of the y-axis. We'll put our point on the x-axis. When there are no x's, that means we have a horizontal line, and we're gonna put our point on the y-axis and draw our horizontal line. Okay, so you have to keep that in mind, because that could happen in your graphing today and/or tomorrow.